Let me introduce our work, Self-Supervised Relation Alignment for Thin Graph Generation. The task of thin graph generation is, given an image, detecting objects of interest and predicting relations among them. One fundamental challenge in thin graph generation is sparsity of data due to a large number of objects, relations, and their exponential cross product. To alleviate this challenge, in this work, we propose a novel self-supervised relation alignment mechanism. Our mechanism is simple, effective, and generic. It can be combined with any underlying thin graph generation model without the need to change the original architecture, laws, or training. We illustrate it with two very diverse thin graph generation models, transformer-based SGTR and LSTM-based neural motifs. This is a general thin graph generation model pipeline. A thin graph generation model usually contains a visual feature extractor to extract visual features, an object detector to detect objects of interest, and a relation predictor to predict relations among the detected objects. The detected objects and the predicted relations then compose a final generated thin graph, on which the training loss is enforced. The green arrows indicate our proposed self-supervised relation alignment mechanism. We create a mirror copy of the relation predictor, which shares network structures and parameters with the original one. Random masking is applied on the input to the mirrored relation predictor to form augmented views of the data. The last largest prediction layer of the mirrored relation predictor is untied from the original one. The prediction from the mirrored relation predictor is aligned with the corresponding one from the original relation predictor. For each element in the input to the mirrored relation predictor, we independently zero it out with probability p. The alignment is achieved by KO divergence between the relation predictions from the mirrored and the original relation predictors. The final training loss is the sum of the model's original training loss and the alignment loss with some weighting coefficient lambda. This self-supervised relation alignment mechanism only exists during training of the model. In the SGTR model, the relation predictor is named as structural predicate decoder, which is a stack of self-attention and cross-attention transformer blocks. The input to the structural predicate decoder is treated as key and value of the cross-attention transformer blocks. We apply the random masking on the cross-attention's attention matrix. We generate one random mask per cross-attention transformer block independently. The last largest prediction layer in the mirror structural predicate decoder is untied from the original one. Here are test results on the visual genome dataset under the thin graph detection setting. We set p to be 0.1 and lambda to be 10. We run the experiment 4 times and reported average results. In the table, SGTR is the original SGTR model. Align SGTR is the SGTR model with our proposed self-supervised relation alignment mechanism. With our proposed mechanism, we can obtain significantly better test results on all evaluation metrics. In the neural motifs model, the relation predictor is composed of an edge context LSTM and some linear layers. We apply the random masking on the input for relation prediction. In the mirrored relation predictor, the linear layers are replaced with an untied 3-layer MLP. Here are test results on the visual genome dataset under the predicate classification, thin graph classification, and thin graph detection settings. We set p to be 0.1 and lambda to be 10. We run the experiment 4 times and reported average results. In the table, motifs is the original neural motifs model. Align motifs is the neural motifs model with our proposed self-supervised relation alignment mechanism. With our proposed mechanism, we can obtain significantly better test results on all evaluation metrics. Here are some qualitative results under the predicate classification setting. The model, equipped with our self-supervised relation alignment mechanism, generally produces more accurate predicate predictions. In this work, we propose a simple yet effective self-supervised relational alignment module that can be plugged into any existing thin graph generation model as an additional loss term. We mirror the relation predictor and feed the randomly masked input to the mirrored predictor. The alignment between the predictions from the mirrored and the original relation predictors encourages the model to learn better representations. Thank you for your attention.